Welcome to ECE 340, which is Engineering Systems Analysis. I believe I just call it Signals and Systems. Hopefully it's the class that you were anticipating. If you were looking for Consumer Sciences 417, it's in another room. It's not this lecture. You can go ahead and get up and leave if that's the class you were expecting. What I want to do to start is make sure that I have you identified and in the appropriate place. I'm going to pass around actually 3 different sheets. 2 will be the same. 2 will be attachment 2, and you just have to sign your name once on that sheet, on that attachment. That's if you are already enrolled in the class. If you are expecting to add the class, then you need to sign your name, not sign, but print your name to attachment 1. So those 3 pages will be going around. The intent is attachment 1 may not have very many names on it. Attachment 2, it doesn't matter which line you sign in. If you've got the other form that starts on line number 38 or whatever, go ahead and start off signing in that particular sheet. That will let me know that you are here and wanting to take the class. I should let you know that there is an assignment, and it's due on Tuesday. It's going to be a challenging assignment, and we'll talk more about that, but it's the passport assignment. It's your passport into the class. We'll talk about that when we start talking about class logistics, which encompasses, and this is how I will start out most classes. I'll have this on the board as you walk in. Question? It doesn't say attachment. This one's blank. So please add attachment 2 to the top. I thought it did, but it does not. So attachment 2 is now going to be handwritten across one of the pages. The other one is typed on the header, and the other sheet should have attachment 1 somewhere at the top. If you're already in the class, do not sign attachment 1. But if you are in the class, go ahead and sign one of those forms that has attachment 2 somewhere on it. We'll have announcements, then I'll try to list the goals, and you can write those down. That will give you the roadmap of where we're headed or what we're trying to accomplish in that particular class. Today we'll go over the class, the syllabus. Most of the material should be on D2L. It just got put on there if you've been checking anxiously looking for homework or something to do. I'll then provide a course overview to try to give you the big picture. Where does this class fit, or what is the purpose of this class? And then we'll talk about a particular system, which is a low-pass filter. I didn't know which projector I would be using or have access to, and so I didn't scale my writing appropriately, but hopefully this is still okay for you as I scroll left and right and up and down in going through this material. Let's now talk about, oh, and I am recording these, or attempting to record. Hopefully they will be recorded. And I will try to make that available to you so that you don't have to frantically keep writing everything down. I'll give you a couple things. One is a PDF of what I write on the screen, and another will be simply the audio-video recording of what's projected on the screen. And hopefully that will be available to you. Let's now talk about the syllabus. I guess I didn't introduce myself. I'm Hal Tharp, a faculty member in electrical and computer engineering, if you didn't know. My office that I will hold office hours in is room 523. That's on the 5th floor of the electrical and computer engineering building. The office hours will be from 9 to 11 on Wednesday and Thursday. And if you can't meet those particular times, send me an email or talk to me after class, and we can try to set something up that will work for our schedules. Lectures are obviously at this time in Saguaro Hall, and most of the material that we will communicate back and forth with will be on the D2L website. And if you're enrolled in the class, you should have access to that particular course, or this particular course, ECE 340, on D2L. 320A is a prerequisite. It hasn't been very well communicated maybe in the course catalog. It's said co-requisite or prerequisite, and it requisites, and it's had semicolons and commas, and if it was read properly, it should have been prerequisites or 320A. I'm not going to worry about 351 or other classes. 320A is the critical class as a prerequisite for this class. Then there's some justification, teaching philosophy, tips for success, and you can read that on your own. There is a textbook. They're saying we don't get enough physical exercise. I went and found the largest book that I could find for this class. Cedrin Smith, well, not for linear systems. And if you couldn't see that, this is what it looks like. And this is a little lighter. That's why I put it on a PDF. I didn't have to carry this with me. But if you're carrying that around, maybe you'll be in better shape by the end of the semester. If you want more examples or worked problems, there's a Shams outline that's entitled Signals and Systems. That's maybe $15. And it has 571 fully solved problems. If you like to see problems solved, you might look for this Shams outline. And obviously that's a different author, but it progresses with the same flow of ideas that we will cover in this class. We are going to start in Chapter B of the textbook, B for background, and then we'll move through chapters 1, 2 rather quickly, and then 4, and now I'm lost. I don't remember exactly where we go. Maybe 6, 7, 8, and 10. It's laid out so that you could cover in a flow continuous and digital information. We will skip most of the digital information in this book. We'll pick it up as we go, but we won't concentrate on progressing linearly through this textbook. We'll start though with chapters B, the background chapter. That should be a quick read, even though it's lengthy, but it should be a review. It should make you feel good about what you already know. That's the intent. And if you don't know some of that material, then you need to make sure that you're comfortable with it as we move through the class. Are there questions so far on the class and the content? In terms of grade, and I was struggling with this all over break. I know break wasn't that long, but I was still struggling with it. How do I do homework? So I've changed it up a little bit. I will make 10 homework assignments, but I'm only going to count your top 8 scores, your highest 8. If it turns out that you didn't do so well on one, or, oh, I can't get that one turned in, 1 or 2 won't hurt you. If you miss 9, yes, that will hurt you. If you miss 6, that will hurt you. It's best if you try to work all of the homework problems and turn those in, but I'm just going to record or use in this percentage your top 8. So I'll just scale that such that 8 homeworks, your highest 8, make up 10% of your final grade. Yes, sir. The homework will be out of the book, correct. And what I may do is I may try to scan the problems, if that helps, because sometimes you might find a different edition. This is the second edition. It's not that critical which edition you use necessarily, although there's been a big change from the first to the second. But the first edition is obviously much less expensive. and the main content will be about the same. But yes, the homework problems will be coming from the textbook. We will have some MATLAB problems. I'm assuming now, if we're on the right path, most of you have now had ECE 310, if you're on schedule. And that's now the introduction to MATLAB. So this MATLAB material, which ECE 340 used to be sort of, oh, let's get our feet wet with MATLAB, that's what you'll be seeing here. These hopefully will be trivial for you, these MATLAB problems. That's the idea. And if they aren't, then you need to get a little bit more comfortable with MATLAB. But we will have some MATLAB problems. The exams are scheduled accordingly, basically about a month apart. And somewhere here I put together a semester on a page to give you a more visual perspective. Where are we? We are now right here, and we will have a few weeks before the first exam. And then because of the structure of February and March, our exams will be on the same day numerically in February and March, and it will be right before you head out to spring break, the second exam. Don't forget everything over spring break. The final exam is cumulative, and we will have a third exam in April 11th, prior to the final exam. And if you're paying attention, and I really want you to pay attention now, that final exam is not on a Tuesday or a Thursday. Even though we're meeting a Tuesday, Thursday all semester, the final exam is on a Wednesday. And it's at 1 o'clock to 3 o'clock. So make sure if you're planning your schedule that you're aware that the final exam is on a Wednesday, even though this class is on a Tuesday, Thursday. And that final exam is on the 8th of May, the next to last day of finals. And it's actually a week after your classes end. Our last day will be April 30th. And the next time we see each other in May will be the final exam, unless you come to office hours. Questions on the structure of the class? If we go back to the syllabus, then here are, have you heard of ABET? That's now just the acronym. It's the accreditation agency that accredits your degree. When you graduate, you will graduate with an accredited Bachelor of Science degree. And one of the things that they talk about are program outcomes. Now they've changed that to student outcomes, same thing, but they have these A through K outcomes. In this class, we will cover quite a few of those student outcomes, A through K. We'll cover A, E, F, I, J, and K. We'll cover them at different levels, but they will all hopefully be covered. As you can see, the passport assignment is going to give us something to do with contemporary issues, whatever that means. Maybe that will become clear through the passport assignment. Here are the class outcomes. These are not as general or all-encompassing as A through K's. These are more specific. These are specific to our course. I've only listed about 35, but by the time we get to the final exam, we may be over 70 or 80 outcomes that you'll be responsible for. And if you know how to work or deal with these outcomes for the course, you should be okay on the final exam. The final exam is comprehensive, and now this gives you a roadmap for where we're headed for the final exam. And you might want to read this over. Maybe every week, just scan it again and say, do I now feel a little bit more comfortable with finding the Fourier transform of a signal? Some of these you should already know. Maybe not, maybe. but I kept it to 33. I wanted it to just fit on one page. This is now essentially how we are working our way through the textbook. This is the topical outline. We're starting with Chapter B, and that's just a review on your own. We'll get into Chapter 1, how do we classify or characterize signals and systems. That's why I call this class Signals and Systems. When is a signal an energy signal? When is it a power signal? Is this a continuous time signal? Is it a discrete time signal? Is it periodic? Is it aperiodic? Do I have a linear system? Do I have a nonlinear system? All of this is important to help us understand what's going on when we're dealing or analyzing with signals and systems. Chapter 2, I've simply labeled convolution. It's much more than that, but that's one of the main outcomes of Chapter 2, which is what happens when you push a signal through a system. Then we'll do a little bit of Laplace transforms via circuits. You should, by the end of this class, feel very comfortable analyzing a circuit. And here I'm meaning circuits that are RLC circuits. Can you now set up and solve an RLC circuit of a generic flavor by the end of the semester and during the semester on the exams? We'll talk about different representations of those systems via block diagrams, Bode plots. Then we'll talk about how do we characterize signals in the frequency domain through Fourier series, Fourier transforms. How do we put all of this into a generic representation, which is, I'm referring to it as a state space analysis. That's Chapter 10. And hopefully this now gives you a feel for how we're moving through the book. We'll then move back into Chapter 8, which is how do you sample, and if we have time, we'll get into Chapters 3 and 5, which are really similar topics that we've already covered for the continuous time case. That's the overview. And before I go into, well, I'm sorry, that's the logistics. Before I get into the overview, let's talk a little bit about your first assignment. It's the passport assignment, so that I can maybe start to put a name with a face. That's the idea. If your name is John Brown, but you go by Sam, Sam would be the nickname that you indicate here. Don't make me try to guess what you are called if you're called something other than your name. And if your name is Jonathan, but you like to be called John, then go ahead and indicate John as your nickname. And an email address. A photograph, that shouldn't be your elementary school picture. Hopefully it's up to date so that I can now say, oh yes, I remember that face in my class. I don't have milk cartons, or that, I do have milk cartons, but I don't have the program that shows you age progression that happens on a milk carton. So if you were well, maybe you can design it after this class. Maybe that's the app that you can write, is an age progression app, so that you can now put in your first grade picture, and now this is what you look like as a junior in college. So an up-to-date photograph, something that's unique to you. I have a lot of students telling me that they ride unicycles, or they do it backwards, or they can walk across the hand, or they can do anything on their hands, basically like we can do walking with our legs. Something that sort of stands out that will allow me to tag a name and a face with that fact. And then there are a couple of questions, 4 and 5. This one is learning styles. This is getting back to the outcomes, the student outcomes. Do you know whether or not you favor being an active or reflective learner, sensing or intuitive? Go to this website, complete the questionnaire, Click on the submit. You're not submitting it anywhere that I know of. It's just categorizing it and then showing how you have indicated your responses. For example, it will have a number line that has active on one side and reflective on the other, and then it will have numbers. And maybe it will place an X above the 7 on reflective. So on your passport, underline reflective and put the number 7. If it actually, for sensing and intuitive, you were number 5 on intuitive, you would not underline sensing, you would underline intuitive and put a 5. Is that making sense? I might try to see what the class looks like as a distribution. Will probably be all over. But sometimes what it's nice is if the class is a lot different than me, then I need to figure out how to think about or understand concepts maybe from your perspective, and you can try to learn how I'm thinking about it, and that will help us all get the material better understood. That's problem 4. And then click on the learning styles description, and it will give you some help or hints on how to use that knowledge to your benefit for the rest of, let's say, this semester and throughout your educational process, which for lifelong learning should be until you retire, right? Which is another 30 or 40 years from now, unless you do really well and then you can retire in 5 years. That's fine too. Then you'll only have to remember it for 5 years. But that's the point of number 5, past, present, and future. And it's about technologies, a past technology, a present-day technology. There's the contemporary issue. Consumer Electronics Show is going on or went on or something. It's pretty quick. It's right now, I think. Anyway, there's an article in Forbes magazine. Click on that link and read this about apps for a car. Ford and GM are now letting the general public develop apps that will work for their vehicles. That's the present question. So after you read this article, talk about, in a sentence or two, what app you would like to develop or see developed for vehicles. In the past category, just answer one of those questions. Which technology is not missed, or which technology is missed? You don't have to do both. That was in the past. And for the future, this is now getting us up to retirement. What technology that has not yet been invented do you look forward to using during your career or lifetime? That's the past, present, and future. And 1 or 2 sentences on each of those time frames, past, present, and future, is all I'm looking for. Is that clear? And then there's a contract. Did you read the ECE 340 syllabus? Signature, if you're putting this in electronically, you can simply type your name. It doesn't have to be your signed name if you don't want it to be. That's your first assignment, and try to do that before we meet again on Tuesday. Questions on the assignment? Let's now get into the fun stuff, which is the class material, and talk about the big picture. What does this course cover, or what are we actually looking at when we're in this class? You should be able to, by the final exam and after today's lecture, at least be able to make the following sketch. And this should be, if you just remember the title of the Shams outline, Signals and Systems, you can make this sketch. It's just signals, input signal, output signal, and a system. Pretty easy. But that's really what we're playing with in this particular class. Here's the input, and that could be single input, it could be multiple input, but in this class we'll concentrate primarily on single input systems. The textbook may label those as x of t. That now is applied or gets injected into this system, whatever that is, and produces an output signal. This class, ECE 340, is a precursor to 3 different technical elective courses: a communications class, a controls class, and a signal processing, actually a digital signal processing class. And let me see if I can sort of give you an idea or a flavor for the signals in each of those 3, what the system means in each of those 3, and what the output signal might look like in those 3 domains of study. If we were dealing with communication, then we might have a signal that looks like that. This is now in the time domain. Here's x of t, and this might just be a message, a 1. You've now discretized potentially a voice waveform, or you're talking on a phone, and now you're wanting to transmit 1s and 0s based on what you've just set into your phone. You now need to communicate that 1, let's say this is now a 1, to someone else. So the signal, the input signal, is the voice or this message. The system is now the channel where that's going. If I pulled out my phone and I called somebody, now that has to be transmitted through the environment or the channel. That may contaminate or change this signal by this very system or nature of where this signal is going. And the output might then look like that. Why? Because there's noise that might contaminate that signal. If it's going a long distance, it might get attenuated quite a bit. So I'll just say it might also get modified. And what we need to figure out is, how do we analyze such a system, such that when you get into the communication class, you know how this works. Now you might say, oh, let me put something in before the signal gets transmitted to precondition it or shape it so that it now looks like a waveform that I can handle or process at the output, so that when it was a 1, I can tell you it was a 1. We need to, in this class, understand this connection. That's for communication. What about control? So let me now try to do a line with the same idea, but now for control purposes. The input signal might look like that. That's now potentially a command. Your system, this might be a command to tell a telescope to move. It might be a command to move a robot arm or a 3D printer. Or it might be a command for a motor to move. And you're now turning that motor on and then turning it off. So your system here could be a lot of different things. It might be an antenna. It might be a telescope. It could be a robot arm. It might be a motor. Those are now the systems that this input signal, x of t, is being applied to. And now what happens? What happens at the output? If this is now some mechanical system, maybe what happens when you hit it with that command is you're telling this robot to move from 0 up to a certain location, well, that robot arm might actually do something like that. It might overshoot and ring a while before it settles down, and then when you turn it off, it actually may ring some more. And now this input goes through this system, generating that output. But if we know the system, how to model it, if we know the input, by this class, we'll figure out how to create the output. And maybe in a controls class, we don't like all that overshoot, or we don't like all of that oscillatory behavior. Question? We will not be talking about PID controls in terms of a controller structure. We will talk about proportional gains, integrals, and derivative action, but we won't put it into a package called a PID controller, which is maybe what we would do in a subsequent class. We might put a PID controller in here, measure the output, feed that back, and create a closed loop system to have the system behave the way we want it to behave. That's another class. But what we have to learn in this class is how do we model the signal, how do we understand the system and model it, and what does that create at the output. Where else did I say this class was a prerequisite? DSP 429, 529. I'm just going to call it signal processing so that we don't have to worry about digital. What do you think the input looks like? The same input structure, right? This could just be a bit. This could be a tone. This is something you now want to process. You're now processing a signal. Whether you do it analog or digital influences the next or the previous modifier to that signal processing. If it's digital signal processing, then you do all this crunching on a computer or with a processor. But in this case, this might just be a tone or even a pixel. And then what you might do in signal processing is you might say, oh, I want to filter that. I want to low-pass filter that, or I want to transform that. I want to compress that information so that I don't have to store everything. I can sort of collapse this down. I can encode that information and make it more efficient. Or maybe you're trying to create some device that has a camera or something, some sensor, and it now needs to figure out where it is relative to an environment. And so it might be important to know what is an edge and what isn't an edge, especially if you're designing an app for a car that's trying to drive, right? That's in your passport assignment. And if we now filter that, suppose we filtered that, what's the output going to look like? And these are all time domain waveforms. Maybe it looks like that. Maybe it looks like a shark's fin versus this very sharp-edged original input waveform. And that's then another class, signal processing. These right now, maybe that's not too hard since you're looking at the T on the axis, those are in the time domain. These are time domain descriptions. We need to also figure out how to work with these in the frequency domain. We're now, or you're becoming electrical and computer engineers. You need to be comfortable talking in time domain, frequency domain, and shifting back and forth. And I'll always be saying, oh, now we're going to go into the frequency domain, or now we're going into the time domain. You need to be comfortable moving back and forth. And that's how we are going to be aided or helped in analyzing these signals and systems. That's our next question. How do we analyze these signals and systems? Well, what was our diagram? Now you can always go back. If you get lost, you can just draw this diagram and try to orient yourself relative to this diagram. Here was our input signals and output, and those are now related by some system. And that system depends on what you're doing. Communicating, control, signal processing, but we now need to figure out what that system is. If we were in continuous time, maybe your input signal looks something like that. This might be, let's say, x of t. If we're in continuous time systems, now we can model our system by differential equations. And once we know the differential equation relationship between our input and output, we can solve that set of differential equations with that forced function or signal, the input signal, to produce an output. So this is now what you could be thinking for continuous time analysis. We will also start to get a feel for discrete time. Because we're going to be doing a lot of this in MATLAB, we have to figure out how do we sample this, or how do we push this into MATLAB, or put this into MATLAB. If we now have this input x of t in discrete time, now we simply have this sequence of numbers. And our time axis might be simply indexed by n. And this is so many samples. First sample, second sample, third sample. Now, instead of differential equations, we now have difference equations. From that, we will then produce some output response, y of n. Up to this point, I've just said, oh, we have an input, x of n. We process that with some differential or some difference equations to generate an output, but I didn't say anything much about this difference equation or differential equations. In this class, we are going to be needing to work with linear systems. So we are going to then, if they aren't already done, we will either have to linearize those or be given a linearized form of those systems. If we have now a nonlinear set of differential equations, we need to figure out, okay, let's now make that linear so that we can play with it, and now we are able to move between the time domain and the frequency domain. Now that we have, and this is what you've been dealing with in 220 and 320, linear systems, if you now had a signal, x of t, and a system described, let's say, by its impulse response, how did you produce the output in the time domain? Do you remember? So the comment was Laplace transform, inverse Laplace transform. I didn't say we could disappear into the frequency domain and then come back. So convolution, if we stay strictly in the time domain, But that's correct. We'll do that in this class all the time. That's what we want to get comfortable with is we start in the time domain. Oh, I want to work in the frequency domain. It's easier because I can now multiply. I don't have to do this convolution integral. But we want to be comfortable with both. If we did convolution, if we stayed in the time domain, then we're doing this convolution where y of t is now this integral from minus infinity to infinity of, let's say, h of tau, x of t minus tau, d tau. That's all in the time domain. If we take it into the frequency domain, by, and I won't put the adjective in front of that, with the Laplace transform is the all more encompassing transform, but we're going to be transforming it with Fourier also, but we'll start with something we're comfortable with, which is the Laplace transform. If we now transform x of t, what does that produce in the frequency domain? Now we just have to capitalize that x, don't we? In the most generic sense, if we take the Laplace transform, we now simply have this capital X of s. Now we've taken this set of differential equations. Maybe they were described by this impulse response, g of t. Now we want to take it into the frequency domain. What happens to g of t? Little g of t now becomes g of s, such that we can now find the output in the frequency domain. Capital Y of s is just the product of g of s and x of s. Because of working in the frequency domain, which we might actually need to talk with respect to our signals, we may want to be talking about Fourier series. If we had periodic signals x of t, or if they were aperiodic, we may want to be talking about Fourier transforms. Both of those tell us information about the frequency content of our signal x of t. But once we have this signal in the frequency domain and we have our system in the frequency domain, now we can just multiply that together. And that's what most students prefer, is multiplication versus convolution, right? Duh. It's easier, right? All we have to do is keep track of these polynomials in S and figure out what's going on. If we now have multiplied capital G of S by capital X of S, we now have this expression Y of S. Which is a ratio of polynomials in S. And that consists of what we will call poles and zeros. Have you heard of poles and zeros before? Now we have this transform that consists of a numerator polynomial divided by a denominator polynomial. The roots of the denominator are poles or zeros. Those are the poles. That's what makes everything go to infinity, right? If you set s equal to 0 in the denominator, that's why it's a pole. If you set the numerator equal to 0 with a value of s, that would give you a 0 value, and that's a 0. If we now sketch that, and these are things that we are going to be doing in this class, if we now sketched the picture, or what I will call the pole zero diagram, that's a diagram in the S-plane. This is now, let's say, J1, this is minus J, and let's say this is -1, -2, -3, and the negative real direction in the complex S-plane. Zeros we will indicate by open circles. Poles will simply be x's. And we will learn that this distance, if you haven't already learned that, this is now our damped frequency. That tells us how those poles that have a component in the imaginary direction, that tells us the oscillatory behavior of that pole or pair of poles. When we have real coefficients in our transform, we are going to end up with conjugate pairs, plus and minus j something. If the x's are our poles and the open circles are our zeros, have you learned about stability yet? Briefly, if I said this is the pole zero pattern or the pole zero diagram of capital Y of S, would you expect capital Y of S to be well behaved? Does that even make sense? If it doesn't, that's okay. We'll learn this. But this is now a system that has poles at those three locations and a zero at -1. If, and here's, so this is very graphical. If you can find the poles of a system, let's say of a G of S, and you can plot those in this complex S-plane, if you can show that all the poles are in the strict left half plane, not on the imaginary axis or anywhere in the right half plane, then you have a stable system. Your poles being in the left half plane gives you a stable system. And we'll talk about that. That's stability. Which is related to the poles of our system, G of S. What's the structure if that pole zero pattern was the pole zero pattern of capital Y of S? Now somebody, let's say you're in a job interview and they say, oh, here's a capital Y of S. What's Y of T structurally? What's the time domain picture going to look like? If they now just give you X's and O's, and this is not a basketball or football diagram with X's and O's. This is now engineering. This is poles and zeros. Yeah. Okay. So you won't see this on TV in that form probably too often, unless you guys make it big and you start talking about poles and zeros on some television show, which could happen. What's the structure of Y of T? Well, what was capital Y of S? Y of S had a pole when the value of S equal to -3 made it vanish. Here I said I had a pole at -3. That means that if I factored my denominator in the transform for Y of S, I must have a factor such that when I replace S with -3, it vanishes. That's a pole. That's a pole factor. I also have two complex conjugate poles. And we're going to learn how to write those in the following form. We're going to say, oh, that now has a real part of -2 and an imaginary part of omega sub d. And so the complex pole combination is now S plus 2 quantity squared plus omega sub d squared. If you look at this, for a value of S equal to -2 plus J1, this will vanish. If you look at this when S is equal to -2 minus J1, this will vanish. Those are now our pole factors for that pole zero pattern that we had before. And this might be, let's say, some, I don't know what, let's just say M times, and where was my 0? That was S plus 1. All right, now this is a review. If I said this is capital Y of S, what's Y of T structurally? Could you inverse Laplace transform this? And you should be able to, if not today, by a week or two, almost instantly, especially now that we've factored the denominator. Now we know structurally what this is going to do or look like, especially if somebody says, oh, well, I can partial fraction expand that, which says that you now have one term that's associated with this pole factor, the real pole, and you have an exponentially damped sine and cosine that are resulting from these complex poles at -2 plus and minus j1. And we can write those as, let's say, some beta times s plus 2 over s plus 2 squared plus 1 squared plus, let's say, gamma times omega sub d and this is now the partial fraction expansion of that. And from this, we can immediately write down the generic structure if you don't solve for alpha, beta, and gamma. You know right away what the structure of y of t, little y of t is. Little y of t is now alpha times what? What's the inverse Laplace transform of 1 over s plus 3? That's coming from the 3, isn't it? That minus 3 is giving us this decay, e to the minus 3t. These other two pieces give rise to a exponentially damped cosine and an exponentially damped sine. The cosine is the beta piece. It's now damped by e to the minus 2t. That was the real part of that complex pole pair. And its oscillating piece has a frequency of 1. That's the omega sub d. These pieces are the result directly of that factorization. And finally, we have the other piece, which is the same damping. This is just now the sine at the same frequency. So that now this 1 is right there, and this 2 is giving us our damping there. And what we want to be able to do is now simulate this in MATLAB. If I gave you this y of t and I said simulate this in MATLAB, you're going, what do I need to simulate this? I need a time axis, don't I? I need the independent variable t. And in MATLAB, I need to tell it how fine do I chop that time axis up? How fine do I sample, and for how long? How long do I have to simulate this before it basically is gone? You could say, well, I know I can simulate that for 1,000,000 seconds. Yeah, you can, and it would be right, but then you wouldn't be able to hardly see your waveform because your axis is so long. And how fine do we sample? That's going to be based on the speed with which we decay and also how fast it's oscillating, moving up and down. And we'll learn how to do that. But the two questions concerning putting this into MATLAB or sampling this revolve around how fine, or maybe I'll answer the first one. For how long do we sample? And then how fine do we sample? Those are a couple of questions we will want to answer throughout the semester. And it will be based on how quickly these decay and how fast it's ringing or oscillating. Let's now talk about something that you've already seen, I hope. When I say a low-pass filter, do you start to see something in your head? Or do you just go, Did everybody get that? So now we have a low-pass filter. Do you actually start to see, or what comes to mind when you hear that phrase? The graph. A graph of what? So a graph of the frequency response, I'm thinking, the magnitude. So somebody might say, oh, I see, so what image comes to mind? Somebody said, oh, I see a graph. And that graph was already in the frequency domain, wasn't it? This is now a frequency domain graph. This is now saying, oh, that's what I see. This is now the frequency response. When somebody says low-pass filter, I now see this picture. That's frequency now, not time. And this might be the cutoff frequency, omega sub c, and maybe this is 1. Maybe I don't want to amplify or attenuate anything in that pass band. This is now h of j omega. That's the magnitude response of a low-pass filter. Does anyone else see anything else? I didn't even hear that. My brain filtered that out. The step response of a capacitor. Or now maybe you're seeing a first-order circuit. What's a first-order circuit realization of a low-pass filter? That's pretty straightforward, isn't it? There's a low-pass filter. Here's R, and here's C. This, let's say, is our voltage out, and this is our input. So we have signals. Here's our input signal. Here's our system, this RC circuit, and here's our output. Signals and systems. You know this stuff. That's a low-pass filter. What's the transfer function between the input, V sub I, and the output, V naught? Or how do we find that? We could find that by voltage divider if we've now mentally put that circuit into the S domain, right? An S domain circuit equivalent. We now have capital V's. Let's call that V out. What's the impedance of a capacitor? 1 over SC. And now if I do a voltage divider, what do I have? I have this impedance divided by the total impedance, which is just a series combination. So my transfer function by means of a voltage divider is the impedance of the capacitor divided by the sum of the two impedances, and that's the transfer function between the input signals Laplace transform and the output signals Laplace transform. And this now you found by means of a voltage divider. Now maybe you've seen it in a transfer function. So somebody saw it as a frequency response, which could be maybe a Bode plot. Somebody else saw it as a circuit. Somebody else may say, oh, a low-pass filter is just this. Well, maybe this isn't very clean. Let's find the transfer function in terms of maybe just polynomials. This is a ratio of ratios. Let's simplify this. Now let's get that over a common denominator so that we now have V out over V in. If I put everything over SC, in both the numerator and denominator, those SC's cancel, and I'm left with 1 upstairs, and SRC, oh, RC is a time constant, plus 1 downstairs, so that we now have 1, we have SRC plus 1. And maybe I will just collapse this into tau, a time constant. This is now my transfer function. And maybe that's what somebody else saw when I said a low-pass filter. Maybe they said, oh, I see this transfer function, g of s, which is just 1 over tau s plus 1, where this tau is a time constant. That's now the transfer function. Did anybody, when I said a low-pass filter, did anyone see a differential equation? We have one hand. Do I see two? Do I see two? Maybe not so common, but now we can go into a differential equation. If we have this relationship with respect to output signals and input signals, and they're now related by this ratio, why don't we just cross multiply both sides, and we now have tau s plus 1 times V out equaling V in. Can we now take this into the time domain? What happens when I multiply by s in the frequency domain? What happens in the time domain? If I had s times capital X of s, and I said, what's that in the time domain? That's the derivative, isn't it? Here I have two terms involving the output. I have a derivative of the output scaled by tau, and I just have the output. Over here, I just have the input. In the time domain, I now have this differential equation. I now have tau dv naught of t dt plus v naught of t is equal to v sub I of t. Maybe you saw that when I said a low-pass filter. This is now a continuous time differential equation. Did anyone see a difference equation when I said a low-pass filter? If I said, oh, here are your 3 exams, and I'm going to low-pass filter them, what am I saying? Here's 3 exams, and I'm going to low-pass filter your exams. I'm going to average them, aren't I? An average is a low-pass filter. Let's see how this can be translated into an approximation of a difference equation and really just show that the input and the output are some sort of moving average. It's a low-pass filter. And once we put this into a difference equation, then we can solve this with Excel. It's just multiplying and adding numbers. It's not having to solve differential equations. We've now approximated this differential equation by a linear difference equation, and now we can just turn the crank. It's maybe an approximation, but if we do it properly, it's going to be a nice approximation. How do we do that? So let's now approximate this. With a discrete time system. Tau is just a time constant. That's just a scaling. That's just a number. Maybe that's 2 milliseconds, which would be 0.002. That scales this. Now, let's go back to our first semester calculus. First semester calculus. How did you approximate a derivative? The change in the numerator divided by the change in the denominator. What's upstairs? That's the output voltage. Downstairs is time. This is just now delta voltage over delta time. That's all we're going to do. And that will be our discrete approximation. We're approximating the derivative. So that now, and this may look a little messy, but now what I want to do is introduce a sampling period, capital T. This now says n plus 1 of those sample periods minus the output one time step before, which is just minus v naught of nt all over the present or future time minus the present time, and that's now my approximation of the derivative. dv dt. That's the first term, and all the other pieces I can just replace the little time, t, by a sampled version of time, which I'm calling little n capital T. So that this now becomes plus v sub 0 of little n capital T equal to v sub I little n capital T, where what I'm doing is in terms of time, I've now sampled that. Here's capital T, here's 2t, here's 3t, and if I do this up here, wow, that's getting pretty messy. This is now, let's say, nt, and this is n plus 1t. That's all I'm saying with my time axis. And I've now gone up here and I've said, oh, here is, let's say, the one time step into the future minus the present time. I can now solve all of this. I can clean this up and get a linear difference equation. What's the denominator here look like? This cleans up pretty nicely. This is nt plus t minus nt. That's just the time interval between samples, capital T. That's all I have in the denominator. This is just the output at this time instant minus the output at this time instant divided by this time interval. That's my derivative approximation. And I'm scaling it by tau. If I do that and push all of this through, I now have tau times v naught of n plus 1 cap t minus, and how do I want to do this? Let me go ahead and multiply by capital T on both sides, and now this is minus tau v naught of nt, and that's equal to capital T, whoops, let me not push that over just yet, plus capital T v naught of nt equaling capital T v sub I of nt. Is that okay? Multiply both sides by capital T, so that gets rid of it underneath these two terms, and it scales now this guy and the right term. That's the capital T. And the tau just enters into those terms. What if I divide everything by tau now and put everything except v naught of n plus 1t on the right? I now can rewrite this and say this now can be rewritten as v sub 0 of n plus 1 capital T equaling 1 minus capital T over tau v naught of nt plus capital T over tau v sub I of nt. This is now a linear difference equation, and what does that represent? What did we start with? Do we remember? This is a low-pass filter. What are we doing? We're taking our present output, it gets scaled, we add in the input that's scaled, and that generates the next output value. We remember that and use that the next time over here, and now we produce the next output, all based on what the input is. This is now just an averaging algorithm. It's just weighting the input and remembering. Here's some memory. It remembers what the previous output was, but it scales that output. This is now a discrete time difference equation. Now we've solved that differential equation with a difference equation. Somebody just has to tell us what R and C are, and that will give us tau. And then we have to figure out how fine we resolve our sampling, and that's our capital T. Once we know that, we can now build this low-pass filter in a discrete setting. Now when I say low-pass filter, you can maybe see the frequency response. You can see a circuit, an RC circuit. You can see, what else? A differential equation, a difference equation. What have we forgotten? A Bode plot, a transfer function. All of those are the same, just in different representations. And that's what we want to get comfortable with in this class. This is now a relationship between signals and a system. The system basically is tau, the time constant. A first order system, that time constant governs pretty much everything. Questions on that? That's the big picture. Keep that in mind as you're working through this material. We have to understand signals and systems so that we can play with it. That's what we want to do in this class. We'll pick up at that point on Tuesday. Make sure you did sign in to an attachment 2 if you are in the class.